Hey,
Long time.
I know.
How are you?
Good, good. Yourself?
Good, good.
Yeah.
Welcome to ISC.
Thank you.
How long are you here?
Through this week,
This week.
yeah, I'm going for a day in between to Hyderabad, but otherwise it's generally around.
Okay, good.
Good evening, everyone. Welcome to the another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Sidharth Jaggi, and he will be speaking on group testing a survey. Professor Sid Jaggi, BTech from IIT Bombay, MS and PhD from Caltech, all in electrical engineering, and a postdoctoral associate in MIT at 2006. And he joined the Chinese University of Hong Kong in 2007 and the School of Mathematics at the University of Bristol in 2020, where he is currently a professor of information and coding theory. His research group, somewhat unwillingly, calls itself Can Do It Team, codes algorithms, networks, design and optimization for information theory. Topics he has worked include sparse recovery or group testing, covert communication, network coding, and adversarial channels. We request the audience, like if you have any questions, please feel free to ask, interrupt the professor in between. And for online audience, please feel free to drop your questions in the chat box and we will relay your questions. Over to you, Professor.
Okay, thank you. Thank you for the invitation. It's lovely to come here. As always, ISC's, I spent a couple of very pleasant summers here when I was an undergrad. I apologize. I'm going to do a little bit of advertisement. So as you can see on the slide, there's something called Informed AI. UK's hubs. It's some large entity by the government for mathematical foundations of AI. And in particular, this one is on the information theory for large-scale distributed AI. So I'm going to do, with your leave, just a couple of minutes of advertisement before I jump into my talk. So yeah, information theory for distributed AI. If you're working on things related to the internet, stock markets, energy grids, like if these are sorts of applications that your research could have, lots of entities working with each other, doing something interesting where you want to compute something in a distributed manner, then we're also interested in that. In particular, we're using the lens of information theory to look at that, but other tools as well, probability, statistics, network dynamics, coding theory, right? So there are people working. So in particular, these, again, it's a little bit of an advertisement, but for example, looking at trustworthiness issues, heterogeneity, impact of the network dynamics, and so on. Oh, hey, Parimal, you made it. There's a bunch of companies interested as well. There are people at Cambridge, Durham, Imperial, we're led by Bristol. And here are some of the people involved. So I know, for example, people here have worked with Ganesh. Maybe you know Paul Inglow, a statistician, Ollie Johnson, and Yanis Kontianis, information theorist. So, so if there's interest in collaboration, there's funding for visits, for whatever. I know Parimal and others are also leading a separate entity, Spark, through which I'm here, right? So anyway, there's funding, right? And come visit us, send students over, or whatever. All right, advertisement over. It's a multi-university thing. It's a so-called hub. So the idea is to network. In particular, CNI is a listed partner, academic partner, whatever that means. I don't know what it means. Yeah. So anyway, but yeah, I mean, generally speaking, if there's interest, we can follow up later. Yeah. All right. So on to the scientific content for today's talk. So this is a little bit of background on group testing for those who may not have seen quite as much, though, for example, Chandra here has worked a lot on it. And then there's, you know, like it's a pastiche followed by a pastiche of different results, different papers. So any particular model I won't talk that deeply about, which is an open invitation for you to ask questions. I don't have to cover everything, I really don't. So I'd really rather listen to questions if you have any. So firstly, a little bit of background. So group testing, you know, it's when I first started looking at it. So you know, let's imagine it was a cute mathematical problem. So let's imagine there's a at that point it was a cute mathematical problem with little applications. Really, an imaginary scenario where there's lots of people, a small subset of diseased individuals, and not enough tests to test everyone, right? And then the pandemic hit, and then suddenly things changed. So you want to identify those diseased individuals. Hopefully there are far fewer than the population, right? And the test you could do would be to pool together different subsets of individuals, samples like maybe saliva, blood, whatever, which is easy to do. Getting the samples is easy, the tests are the precious resource. And with these appropriately pooled tests, so for example, if you test someone, test a pool of people, and that pool reports a negative test outcome, then you don't need to test anyone from this test later, right? So that will save your number of tests. So the information theoretic limits for this. So intuitively, like if you think about it, the way I posed a problem, if you know that there are small d diseased individuals, so that information is available to you, right? The d is known, or a good upper bound in it is known. Then the number of subsets that are there is n choose d, right? Let's say it's uniformly spread over all n choose d subsets. And therefore, even just to write down the answer would take the logarithm of this many number of bits, right? And each test is like a bit, so you're only getting one bit of information per test. So via relatively standard information theoretic lower bound techniques, you know, even if you allow epsilon probability of error, you'd need log of n choose d number of tests. Stirling's approximation when d is much less than n, that'd be d log n over d, right? So that's an information theoretic lower bound on the number of tests required, right? Now this holds whether you have non-adaptive tests or adaptive tests. So, and as the phrase itself sort of suggests, so adaptive would be you do a test, you look at the test outcomes, then you do the next test, and so on, right? So you do them sequentially.
So information threat limit is because, so you said what is the goal? Goal is to get the subset of everyone who's infected. Is that the goal?
Yeah, so as phrased, the goal is to identify precisely the set of diseased individuals, right?
So you see that there's a D subset, then you get lucky if you choose exactly that one subset. I'm assuming that all D subsets are uniformly at random.
No, so the point is, even to describe which of the n choose d subsets it is, right? Well, even just to write that down would take log of n choose d number of bits, right? And each test is giving you at most one bit of information, right? in principle, multiple tests could have overlaps, could have correlations. So information theoretically, it may actually take more than this many number of tests. We'll see this shortly, actually, right? So this is just intuition. You can formalize this via the usual thing, Farmer's inequality, blah blah blah, and
But you would not necessarily choose a D size subset, right? So you
you
would
don't.
actually choose something as D prime.
Indeed, and in particular, in the next few slides, I'll ask you to build intuition about what the group size is. Actually, now's a good time too. Does anyone have intuition?
I would think that initially I would be choose large subset just to get, but I do not know how the biology of this works, because if you take large group size, maybe this gets diluted, the signal, right? But I don't know if you're considering that.
Yeah.
But if it was not the case, I would try to go large and then try to identify that.
Okay, very good. So you've brought up several things. So yeah, the biological implications, maybe things get diluted, we'll talk about later near the end, right? So different types of noise and dilution and so on. Right now, it's a classical thing. You do a test, like a clean mathematical model, you do a test. If there's even a single diseased individual in the test, you get a positive outcome. If there are none, you get a negative outcome, no noise. That's the classical model we have right now, yeah? And your intuition about maybe going large. So let's examine that a little bit. Yeah, okay. Let's come back to this slide. Let's come back to the slide. Let's actually build that intuition right now. So where was it? I thought I had. Okay. Well, actually, yeah. Okay. Maybe let's wait, because the order to the slides, then it gets messed up. I don't know which slide is. So yes. Okay. Very good. So there are multiple models for this. One model is the set of D diseased individuals is uniformly spread. So there are n choose D sets uniformly thing. Another model is the probability of a disease model is IID with probability P. So maybe you're thinking the probability of a diseased individual is D over N, right? So to draw an equivalent between these, the probability is D over N, because then the expected number would be D, right? And but only expected. It could be less, it could be more, right? Binomially distributed. In many, though not all settings, well, most settings, those two models behave similarly, and both of those models, the fundamental lower bound basically ends up behaving like this, right? Because n times h of p for your setting, when you do Stirling's, or when you take the corresponding limit, substitute in p as d over n, d is much less than n, then you end up with again d log n over d, right? All right. So yeah. False alarm or missed detection, both are incorporated in here. And they're not necessarily symmetric, so you have to balance that as well, right? So that's a fair question. A related question is, what if you demanded zero error? And there it's an entirely different problem. It's a combinatorial problem with very different scaling laws. D square log n, roughly speaking, is the number of tests required, as opposed to d log n, right? So I will not talk about zero error testing at all. Yeah. The probability of error is, you can view it equivalently. It's either over the choice of how do you test, or it's over the set of diseased individuals. That sort of, you can translate one probability to the other. Okay. Now a little bit about adaptive versus non-adaptive. So as we were saying, so when you first pose this to undergraduates, which I often do, this is my favorite tutorial activity, like for an open day, we have undergrads coming in wanting to do math, and we offer them tutorials because that's what mathematicians do apparently. This is a favorite problem to toss at them, and their minds immediately go to the adaptive setting, right? You test some subset. If it's positive, then break it up. If it's negative, then choose some other subset, right? and that is inherently adaptive, right? Which is a natural way to do things, but in a world where each test takes a certain amount of time, right? Like if you're testing literally, or if you're doing some industrial testing and so on, doing it sequentially costs time, right? And therefore may not be desirable. You may want to do things in parallel if possible. And in some settings, you don't lose much or even at all if you do things in parallel. So that's the non-adaptive thing. Designing these non-adaptive things is trickier, analyzing the results is trickier, but that's maybe more desirable, right? One other question which often comes up right in this slide over here is, well, here you're assuming you know the value of D, What if you don't know the value of D, right? And there are various answers here. So for instance, so it turns out finding the value of D, if you do it adaptively, is not hard. Okay, let's wait on that question until a few slides later, when we'll see how you estimate the value of D if you don't know it in advance. Okay, I'm getting a lot of questions. This is wonderful. Any other questions before I start moving on? Okay, good. So yeah, this slide is basically saying what I've already said. So yeah, even just log of n choose D behaves roughly like d log n over D plus a lower order term, adaptive versus non-adaptive, and mostly I'll be focusing on non-adaptive. Yeah? Okay, so for non-adaptive schemes, one convenient way of representing these non-adaptive schemes is, yes. Yeah.
Number of bits to represent, right? You said these number of tests you need at least to get one bit.
Right. Yeah. I mean, it's or again, if you're describing to undergrads, one way of doing it is, imagine doing your first test. It's a positive outcome or a negative outcome. You do your next test, positive outcome, negative outcome, right? So after T tests, you have a tree of a certain depth, 2 to the T. And if 2 to the T is less than n choose D, then pigeonhole principle, you'll have some problem, right? So that's an intuitive way that sort of lets people understand that, okay, if 2 to the T is less than n choose D, then there must be at least two subsets with the same set of test outcomes, and therefore you'll have problems, right? Okay, very good. All right, so coming back to how to describe non-adaptive tests. So one convenient way, this is just notation almost, but it'll show up for the rest of the talk. So just to introduce that, is via matrix, where each row corresponds to a test. So for example, ones correspond to item number 3, 4. By the way, so I started by talking about group testing with individuals and diseases. A different context is items in an industrial setting. Some of them are defective. Sometimes I'll switch between diseased and defective, right? By no means I'm implying that people with diseases are defective, right? It's just if I slip, then so I apologize in advance, right? So anyway, you have a test over here. So let's say the third, fourth, and whatever these individuals are included in the test. But for example, the first and second are not included in the test, right? So this ones basically means inclusion or and zeros means exclusion from a given test, right? That's what this notation is saying. And correspondingly, like columns correspond to individuals. So in this case, maybe the oracle knows that the third person is disease-free, whereas this person has a disease, right? Okay. Yeah. So this is basically what. Yeah. So I've already said basically what's on the slide.
So once again, you said the disease person, or it's not.
Yeah. So a priori, when you're designing these non-adaptive tests, you have to design this matrix. You have no idea who the diseased people are, who the disease-free people are. Inclusion and non-inclusion. Yeah, notationally it's a little bit confusing. So the test outcome vector, which is the also a vector of the same length as the number of rows of this matrix, is also often represented as a 0, 1 vector, and the disease status is also represented often conventionally as a 0, 1 vector. Really, these are somehow different sorts of objects, right? And ideally, we would have, like for example, test outcomes should be plus minus, maybe notationally, right? And the vector should be, I don't know, disease, disease-free, something like that, right? But everything is 0, 1, the common notation, yeah? Okay, so now we get back to one of the things we had started talking about. So when you're designing your tests, how large should you make your tests, right? Now, as maybe your intuition was, well, if you make your test, so if you make a test too small, then, well, very likely it'll be a negative test outcome, right? And you'll not learn too much. On the other hand, if you make it too large, maybe the whole population, then, you know, it'll be positive, right? And again, you haven't learned too much. So there's a right scaling somewhere in the middle where the probability of a positive test outcome should be ideally close to a half, right? Because then you're getting 1 bit of entropy per test outcome, right? So the right scaling for that is, it's not too hard to convince yourself that you should want a matrix density with roughly 1 over d, right? Like roughly 1 over d items in the matrix should be tested, right? Or equivalently, the number of items tested in any test should be roughly n over d, right? Why is that? Well, if it's n over d or some constant times n over d with some elementary probability, you can convince yourself that the probability of a positive test outcome is constant. It's
So I'm not getting this. So you have a matrix, right, which has n columns, which is fixed, and in how many rows, which you have not told.
yeah. So I haven't told you the number of tests yet.
But you are still saying that without that, you can always say that n by d of them are 1, because now it's n cross unknown, zeros and ones, right?
Yeah. But what I'm saying is, suppose for every row, which is a test,
For every row, you think n by d should be
roughly n by d should be ones. Why is that? Because again, if it's too dense, then mostly positives, too sparse, mostly negatives. So the right density, I'm claiming, is roughly n over d items per test. Why is this? Because, well, like with a little bit of elementary probability, if it's n over d, then the probability of a positive test outcome is 1 minus d over n to the n over d, like if this is my group size, right? So this behaves as e to the minus 1, roughly speaking, right? So with the right, instead of n over d, if you do n over d ln 2, then you get a half, right? So that's why that's the right scaling for this problem, right? And this is purely by entropy considerations. If individual tests are to give you as much information as you'd like, then this is the case. Now, in some settings, as I'll discuss later, you don't have this luxury. Maybe it's demanded that your test sizes be too small, you know, the physical apparatus can't handle something too large, or each person can only be tested a few times. Again, you can't give blood so often, right? So because of those considerations, then you can't get 1 bit per test, and then that changes the scaling of the problem, right? So that's, and I'll talk about this in a different model. Now, this slide is maybe also the place where we talk about, okay, so as we said, the right scaling to get sort of a constant probability of a positive test outcome is group sizes n over d. So if you did not know the value of d, if you wanted to estimate the value of d, maybe that's your problem, not estimating who the individual is, but just estimating the value of d. So this suggests a way of doing it, which is the following. So, you know, let's say you choose a group size of 1, choose a group size of 2, choose a group size of 4, choose a group size of 8, 16, exponential scaling, right, until n. And there are roughly log n such group sizes, right? Repeat each test a few times. For the small group sizes, mostly you'll get negatives. For the large group sizes, mostly you'll get positives. Somewhere in the middle, you'll start getting a phase transition, right? And that group size will be roughly n over d, right? For large n, for large d, or whatever, yeah, well, so you can concentrate the behavior with some tweaks. You can make it a pack algorithm, probably approximately correct algorithm, right, with a given approximation factor and so on. So with log n tests, you can figure out roughly the value of d, right? And this is, by the way, non-adaptive. If you wanted to do it adaptively, if you had the power to do it adaptively, then you could just do binary search on the logarithmic scale, and then log n test would suffice. Right? So the simple observation that n over d being the right group size for seeing something interesting already leads us to algorithms which are known, published for how to identify the value of d. Right? So you could imagine doing this as a precursor to whatever the group testing algorithm is. That's one possibility. The other possibility is, well, okay, maybe you don't want to, maybe you really want to stick to something non-adaptive, right? But you don't know what the value of d. How do you design your tests? So you could do the following. You could say, well, I don't know the value of d, but first let me be optimistic. Maybe d is 1. Design some tests according to that. Then maybe less optimistic, d is 2. Design some tests corresponding to that. D is 4. Some tests according to that, and so on. Now here's the thing. Because the fundamental scaling for a given value of d behaves basically like d log n, let's say. So let's say you do 1 log n test for d is 1, 2 log n test for d is 2, 4 log n test for d is 4, and so on. So you're summing up a geometric series, right? And by the time you hit d log n tests, that's only a factor of 2 that you've paid in designing the sequence this way, right? So even if you don't want to do a precursor step, but you somehow have a rateless setting where once you get the right answer, you stop, right? Then this is also doable that way. Yeah. So identifying the value of d is not really a bottleneck in this setting. That makes sense? Okay, good. All right. So yeah, and there are different ensembles. You can yeah, yes.
Looking at the outcomes, the test outcomes, how do you know if you got your D right or not?
So that depends on your algorithms, right? So there are various recovery algorithms. So far I haven't told you how to analyze these. So various recovery algorithms, one of which is coming up on the slide shortly thereafter, will come with a guarantee, a probabilistic guarantee. The probability that if your tests were chosen from the right ensemble, the probability that your recovery algorithm did the right thing will be such and such. Is that a satisfactory answer?
No, that's not my question.
Sure.
So you don't know the value of D, and
Okay.
you've gone up to some value of D and you've designed your test, and you have a set of test outcomes in your hand.
Sure.
But if you've not gone far enough in D, by looking at the outcome, is there a way of knowing that you failed?
Sure. So for example, the scheme that I just suggested with first a small matrix with D is 1, a slightly larger matrix with D is 2, and so on, right? That has the same property as the scheme we just suggested for estimating the value of D, right? So now you could imagine using the same test outcome vector for two purposes. One, to estimate the value of D, and two, assuming you've chosen the right value of D near the bottom, then to decode it, right? So that same vector can be repurposed for both of these things, and that's good enough.
But will you also be able to say whether your D is beyond the highest D you went up to?
Right. So if you do it in the way I suggested, then most test outcomes will be negative, right? And therefore, very likely you did not go far enough, right? Because the de-estimation algorithm comes with its own probabilistic guarantees, right? So it'll give you, were you up to a factor alpha close to the correct value of D with probability beta, and for choice of alpha beta, right? I'm hiding some things under the rug, how many times you repeat these tests and so on, but in morally speaking, the algorithms behave kind of like this. Does that make sense? Good. So remember we said the scaling is the number of items per test is is not D, it's N over D, right? So if the single diseased individual, it'll be, now actually it should be N over D plus 1, or that constant factor times whatever should be there, right? So basically you'll be testing roughly N over 2 items per test if there's just one diseased individual. That makes sense? Now how do you design it? Well, so there are various ensembles. So one ensemble is to test that the one that is most often considered in the literature is to test each item with probability theta 1 over d, right? So you just choose this matrix randomly, theta 1 over d. Slightly better results are obtained if you instead fix the column density to be a certain amount, theta log n over d. This is the same expected behavior you would get if you'd be choosing items with density order 1 over d. But if instead you enforce this, you don't allow the variation in the like the binomial tails, then you have slightly better performance. Yeah. Okay. Good. I really like the lots of questions, and again, if I don't cover everything, that's entirely fine. Anything else? Okay, good. So, okay, so then, here's, this is a slightly outdated slide, but here's the state of the literature. So what is this saying? Okay, so firstly, along the x-axis, so think of this as being, the x-axis being like d. So one parameter regime of interest is when d itself scales with n as some polynomial. For example, square root of n to the 1/3, and so on, right? So that's why I enter the theta. The y-axis is somehow a normalized rate. So what is it measuring? So I hopefully convince you that d log n over d is a fundamental bound. You can't hope to beat this, right? You have to do at least this many tests. And now whatever your algorithm is, maybe whatever it is, it has a certain number of tests, use that as a denominator. So divide d log n over d by that. Now this quantity, therefore, cannot be greater than 1, right? The number of tests you use has to be at least the fundamental lower bound if you want to have a high probability of success. And the closer you get to 1, the better, right? So it turns out the information theoretic limits, and so that's why I ignore the side thing, it's a little bit outdated. The information theoretic limits are known to match the counting bound up till something like n to the 1/3, and then fall down like this. So in particular, as you get to d behaving like n over log n, then it turns out that individual testing starts becoming optimal. If the number of diseased individuals is too much and you demand a probability of error going to 0, right? No fixed probability of error, but probability of error going to 0, then n over log n, more than some constant times n over log n, you need to do individual testing, no coding gain, right? But in between, there's this interesting sort of behavior over here. Yeah. And relatively recent work by some groups in Germany, there are efficient algorithms that attain this curve over here as well. Yeah. So this is all just in the classic group testing setting, no noise and so on, and non-adaptive. Adaptive, the setting is easier. Again, I'm not talking that much about adaptive, but if you cared about adaptive group testing, then you can basically stay on this green curve, the information theoretic limit, throughout, right? Including in the linear regime. Well, in the linear regime, maybe you pay a very small constant factor price, but you're quite good. Okay, good. All right, so moving on. Yeah.
So this theta increasing is the more and more effective, right? And we say when adaptive you get rate 1, what is that?
So that means with d log n over d, so remember in this graph over here, this quantity, the numerator is d log n over d. So rate 1 means with that information theoretic limit number of tests, you can basically, for almost all d, hit the limit.
D log n by d is information theoretic. What is the denominator?
So the denominator means you do your best. There are different algorithms listed over here. Yeah.
So you're saying for what did we say, for adaptive, the best is D log n by d.
Yeah, so there are schemes. In fact, even the schemes you would think about if you thought about it even just a little bit, sort of divide and split and so on, right? With some slightly careful choice of group sizes, but yeah, those. And again, we'll see some version of that later. Yeah. Okay.
So what it tells you that the gain is only to be had if you're not doing adaptive.
Well, so in this classic model, what do you mean by the gain is only to be had?
I mean, in group testing offers, so the only offers you, so what this is less than 1, right? So less than 1 means, binary tests is larger actually than information theory problem, right? For all these algorithms.
So once you get beyond n to the 1/3 for some reason, then you start getting away from. So then you would gain if you were allowed to use adaptive tests. You would require fewer tests.
So the adaptive test is the best if you go beyond this 1/3, right?
Right. And the suspicion is it's a similar. The story in noisy tests is less clear, but the suspicion is the story is similar. Partial recovery is slightly different. So the variants start getting interesting, have their own particular behavior, right? So here, think about it as purely adaptive versus non-adaptive, noiseless, just that's the only story I'm telling so far. Yeah? Okay, good. All right, so just to get our hands a little bit dirty, let's even see how one of these algorithms works, right? This is going to be far from optimal. It won't hit that information theoretic curve or something, but it's easy enough to present on a slide, so why not? Just so we get our hands dirty. So we have some n items, some t tests, we'll specify t shortly, and we have some set of test outcomes. And we designed this matrix, let's say Bernoulli D, right? Bernoulli D, Bernoulli 1 over D. So the probability of an item being included is, let's say, 1 over D, right? And now what will our decoding algorithm be? It will be a simple greedy decoding rule. So if an item only appears in tests where the test outcome was positive, then it's not an unreasonable hypothesis to guess maybe this item is defective, this individual was diseased, right? It may not be. It might be that the set of positive test outcomes, like the diseased individual somehow masked this individual, right? Every time this person was in a test, there also happened to be another diseased individual. It could be the case, but we're just going to, push our luck and maybe just use this as our decoding rule, right? And on the other hand, if item individual is in some test where the test outcome is negative, even one such test, and again, we're thinking noiseless right now. There are ways to make this noise resilient, but right now noiseless, right? In this case, we'll say not defective, not diseased, right? So this would always be correct, right? We won't make a, in a noiseless setting, we won't make a false negative, right? If it's negative, like if you're outputting it's negative, then we are doing the right thing, right? If you're outputting it as positive, we might be making a false positive outcome determination, right? So it's a one-sided error, this decoding rule. So we just have to analyze the probability of a false positive, right? So so the decoding philosophy, guilty unless proven innocent, right? So anyway. So let's say the number of tests we choose is some constant times d log n over d, right? We're not trying to hit the information theoretic limit, just getting to a constant factor will already be good enough for our purposes, right? And let's say that the density was chosen, so it's some alpha log n over d, right? The weight of a column. So the fraction of negative test outcomes by a similar calculation as this is going to behave as some constant, right? E to the minus alpha over c, right? So therefore the fraction of positive test outcomes is 1 minus this quantity roughly. So now the probability that an item I has a false positive is going to be, well, the fraction of false positives to the times, so what is this quantity over here? It's just c times, so alpha log n over d is just alpha 1 minus theta log n, right? Because d we assumed is n to the theta, right? So then the probability of at least one false positive union bound, right? Just multiply by n minus d behaves kind of like this. And then you therefore just need to find a c, so you can find a positive alpha. So if you choose alpha to be this, c turns out to be something like this, okay? Again, I went a little bit fast just to prove the point that at least for a relatively simple algorithm, you're already not getting too bad behavior. You're up to a constant factor, in this case 1 over ln 2 times the optimal answer, right? Okay. All right. I mean, these slides will be available later, and I'm also happy to chat later. Okay, quite slow, that's fine. So what is convention? When does one stop usually? So 6 o'clock with no time for questions. I mean, I can stop 5 minutes early if needed. Okay, okay, good. All right, so let's start getting to stuff where I beat my chest and talk about some nice algorithms we designed, right? So okay, faster algorithms. So what does this mean? So if you think about this algorithm where we have this greedy decoding rule, right? Well, maybe I went too far, but remember we check each column of this matrix to see whether its support is included over there, right? So somehow the computational complexity for this algorithm, you have to check every column of the matrix. It's going to be at least the number of entries in this matrix, right? It's going to be at least n the number of individuals times the number of tests, right? Can we do better? Can we do better, right? And one intuition, not a precise intuition, is like, for example, if you're doing binary search, you don't have to check every individual. You can do logarithmic in the size of the thing, right? So can we get such an exponential speed up? And indeed we can, right? We indeed can. Yeah, like the naive sort of algorithm I talked about is somewhere over here. There are faster algorithms, but non-optimal. So what we want is somehow to be close to optimal in the number of tests and the decoding complexity, or wrong, pointing at the wrong things. But decoding complexity, we want to be quite fast. Number of tests also, we want to be quite fast. Clearly, you can't hope to do less than d log n, right? Because the number of diseased individuals, well, even writing out the answer would take d log n bits, right? So you can't hope to do faster than that, but can you get close to that? Yeah. And yeah, 3 different algorithms. I probably won't talk about all of them. They have overlapping ideas. So, but yeah, different performance. So here's one sort of hammer, which is quite useful. So first let's describe sort of like a module that would be useful to have, right? We'll talk about how to construct this module later and how to use this module later. But first, let's just define this module. Like this will be sort of a subset of the types of group tests I'll be doing, right? But I'll be repeating this subroutine many times. So what is a subroutine? It says, so given, so maybe your full population has some capital N items. By the way, I apologize for repeated changes in notation. So in this set of slides, which again I've stolen from different talks, so slightly differing notations. So in this set of talks, in this set of slides, like the number of individuals is capital N, the number of diseased individuals is capital D. But in this little subroutine, so it's given a smaller subset which has some small n individuals, so a subset of all the individuals, and therefore a subset of the diseased individuals, right? And what is this subroutine output? So it has sort of 2 sub-subroutines. One subroutine gives the multiplicity roughly. What does that mean? If this value of D is 0, if there are no diseased individuals in the subset, then it tells us that. If the D is bigger than or equal to 2 or more, it tells us that. And then the most useful case is if D is equal to 1. So if there's precisely one diseased individual in this subgroup, then it does more. Instead of just telling us the number of diseased individuals, it also tells us the identity of this diseased individual. Yeah, and it's able to do all of this with a relatively small number of tests, with order log n tests, and with decoding complexity also order log n, and the error probability 1 over poly d. Okay, so this will be a very useful module in everything that comes later. Okay, so firstly, multiplicity testing. So this is related to that idea we talked about earlier, which is, if you have the right group size, then you can infer the statistics of. So for example, if there's a yeah, so suppose we just choose some random sets with Bernoulli half tests, right? Bernoulli half. So in the subset, we are choosing random subsets of size half the subset size and testing them, right? So if there are no diseased individual, well, every test outcome should be negative, right? If there's a single diseased individual, half the test outcome should be positive. And if there are 2 or more, then the fraction of positive test outcomes should be 3/4 or more, right? Here I'm assuming noiseless tests. Actually, even if they're noisy tests, the statistics are slightly different, but you can again like do the usual expectation, concentration, and so on, right? So hopefully I've convinced you multiplicity testing is somehow easy. You can infer, if all you care about is 0, 1, or 2 or more, right? Then it's somehow easy to do this. You can do multiplicity testing. How about, yeah, there's a usual more explanation. How about localization? So, so in the noiseless case, it's easier, but let's even consider the noisy case. You have noisy tests. You can't necessarily trust every test outcome. So in this case, maybe the columns of your localization test matrix are code words of an error correcting code, right? So they somehow look very different, yeah? So if so, now you get some positive test outcome vector, and then you just do somehow maybe minimum distance decoding and figure out, because if it's just a single diseased individual, if there was no noise, it should be precisely a code word, right? It should be precisely one of these columns, so it should be a code word. So you're basically doing error correction and trying to figure out which column it is, right? And now expander codes have these really nice properties that they have decoding complexity that's linear in the block length, right? So that's why if you use code words of expander codes, then you can decode in time very quickly, in time order log n things, okay? So that's how you design this object. So you can figure out in order log n tests and complexity and probability of error 1 over poly n which individual it is. Yeah? Okay, now how do you use this? So let's use an example for let's say adaptive tests. Okay, so we have now capital N items, capital D diseased individuals, defectives, and suppose we partitioned it randomly. Then so if these partitions were of size n over d, then a constant fraction of these subpartitions would have a single diseased individual in them, right? And then if we use grotesque on each of these subpartitions, right, then we can figure out which diseased individual it is. But not all of them would have 1, right? Some would have 2, some may have 0, right? So there's that as well. So the point is, okay, in the first round, you've gotten with order D of these partitions, right? You figure out a constant fraction of the diseased individuals. Now you repeat, so you remove the ones you found out, and you repeat now, but now with order D over 2 of these groups, with order D of 2, D over 2 of these partitions, and then you repeat, right? And it decays geometrically, right? So overall, with roughly D log n of these partition tests, you can do it, right? But yeah, so, and then eventually, when there are very few remaining ones, very few remaining diseased individuals, then at that point you just default to using a very coarse granularity and doing tests that way, right? At the tail end, you have to do something else. And you can do the same thing with non-adaptive group tests. In this case, you do these partitions in parallel, right? In this case, you rely on coupon collection. So maybe in one set of partitions, you collect some constant fraction. Another set of partitions, constant fraction. There'll be some overlap, but by coupon collection, after you've done this enough times, then you'll have collected all of them, right? And two-stage adaptive, we rely on the Berde paradox. So first, we group them together into these little subgroups, right? Each subgroup is now viewed as a single individual, right, on which I can run the grotesque algorithm. So and then I'm testing these subgroups. So by the Berde paradox, if I choose something like order d cube of these subgroups and then do whatever, the exact parameters might be a little bit mysterious, but really basically trust me, like all the standard things you learn in a first year undergrad's algorithms course, right? Coupon collection, birthday paradox, blah, 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 like all of those sort of can be combined very nicely to get these fast algorithms. Okay. All right, so 55, huh? So I have time maybe for one model, and then I'll sort of buzz through super fast in the remaining two, right? But I'm happy to talk. I'm around for the rest of the week, so we can always do that. Okay, so this is a setting with constraint tests. So, so maybe you want to. So maybe you have a real world limitation in this case. Maybe to collect your samples, this vampire can only bite a few people, not too many, right? So, so each item can be included in at most a certain number of tests, or maybe each test can have at most a certain fraction of items in it, right? Maybe these are examples of real world limitations. So in this case, the scaling laws are fundamentally different. So for example, if each item can only be divided some gamma times, right? Then instead of that d log n over d behavior we're used to seeing, it becomes quite different. So it becomes gamma d times effectively something like n to the 1 over gamma. Okay. So as an example, just to wrap our heads around it. So suppose each item can only be tested twice, then the scaling law becomes something like d times square root of n, right? Ignoring the epsilons, and the epsilon is the probability of error and so on. So square root of n, of course, is much larger than log n, right, which would have been the corresponding factor there. And there's a deterministic algorithm which is not too far off. Okay. Yeah. So this is an algorithm, and then the information theoretic bounds basically match this up to small factors. So in this case, not up to constant factors, up to small polynomial factor, polylog factors. I forget what the latest state of affairs is. Yeah. And similarly, in the row setting, where it can be included in row size tests, again the scaling laws are n over rho times something like this. Yeah. So the algorithms are actually very similar to what we had before, right? So for example, I talked about choosing a matrix with the right density, right? And then we did some analysis. Essentially the same algorithm basically works, but now you just have to choose from a matrix with the right density, right? Like for example, if each item can only be divided gamma times, what is that saying? Each column of your matrix can only have gamma 1s within it, right? So that's the ensemble you have to work with. If you do that, and then you basically replicate the analysis that we did, union bound, blah, 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 then you get this behavior. Okay? I went too fast for you to examine that proof, but that claim, but really it is very similar to that. Okay. There's a deterministic version as well, which has some nice intuition. So for example, again, consider the setting where, let's say there's a single diseased individual, and gamma is 2. You can test every individual twice. So in this case, what might you want to do? Arrange the individuals in a grid, in a square grid, and test every column, test every row, right? And then the diseased individual will be precisely the one who sits at the intersection, right? So this is 2 times square root of n tests, and that's, I claim, order optimal, right? Gets a little bit trickier when you have more than, like even if you have 2 diseased individuals, you test all the columns, all the rows, now you'll have 2 columns, 2 rows, 4 intersection points, right? So you somehow have to disambiguate the intersection points. There's some further ideas, random subsampling, blah, 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 right? But effectively, there are deterministic designs also which are very nice over here. Yeah. All right. Okay, I'm going to skip this. Lower bounds, it basically comes down to what we talked about. So you could imagine, so remember we said, ideally you'd like to try to get 1 bit of entropy per test outcome, right? But to do that, your tests have to have density, have to have size, weight, roughly n over d, right? Because if it's much less than that or much more than that, then your probability outcome is skewed, entropy is far away from 1 bit. So, but on the other hand, for example, in the gamma divisible setting, you may not be able to do that, right? Maybe some tests, which we're calling heavy, can have maybe a density close to that. But there must necessarily be a large number of light tests, right? And just by some basic counting argument, you can argue at least a certain fraction must be light, and then for a light test, what is the overall entropy you can get? And this is too fast. These slides are useless. But basically, you can argue that for the light test, the entropy you're getting is not very large. It's something like gamma d log t over gamma d. You choose your parameters carefully for what does heavy mean, what does light mean, and then the amount of entropy you're getting per light test is not very much at all. So you reverse engineer the calculation a little bit, you end up basically being very close to the achievability. Okay. Again, I apologize. These slides are firstly badly made, secondly I'm going slow, fast. So okay, now lightning fast, right? A few generalizations. So so one generalization is related to what you had said, like maybe you have dilution noise and so on. So in this model, maybe your x-axis is the number of diseased individuals per test, and the y-axis now is a probability of positive test outcomes. So some monotonic function, right? So as the number of diseased individuals in your test increases, then the probability of a positive test outcome increases. This is one model which is on the slides. Another model, more recent, not on the slides, is x-axis is the fraction of diseased individuals on the slide in a test, right? Because that more accurately captures dilution, right? And y-axis is the probability of a test outcome, again a monotonic function, right? And we have results basically order optimal in both these settings with very different scaling laws. It turns out knowing the number of diseased individuals in a test is very different, gives you more information than knowing just the fraction, right? The fractions are much harder, you need many more tests, right? But in this case, if the probability of a positive test outcome depends on the number of diseased individuals, like you basically use the slight. So if an item is included in a test, the for test and it is, let's say, diseased, that individual is diseased, there'd be a slight subtle variation in the fraction of test outcomes in which this participates, as opposed to if this individual was disease free. So that slight difference between the probability minus q and probability plus q, this basically are the corresponding binomials corresponding to that individual is negative or positive, right? So then just by concentration inequalities, you can sort of separate these probabilities out and therefore infer the probability of positive test outcome. Yeah. So with all of this in mind, for a general monotonic function, we can, some complicated things here which don't necessarily bother us, but we have upper and lower bounds on the number of tests. These lower bounds depend on the function, depend on the shape of the function. But basically, the ratio between these upper and lower bounds is at most order close to d, so d to the 1 plus epsilon, right? And oh, by the way, in that other model with the fraction of diseased individuals, very different scaling behavior. Instead of something like d log n times at most d, there it behaves like n over d to the some alpha, that alpha is somehow the slope very close to 0, right? Because the behavior, because most tests will have roughly d over n like expected fraction, right? And therefore the behavior is quite different. You can find all of these on archive or wherever. Final model, prior statistics. So suppose, so we began by assuming each set of diseased individuals is diseased with probability, with equal probability, right? So therefore 1 over n choose d is the probability of every subset, right? Or I claimed equivalently the probability of every individual being diseased is d over n, right? It's not immediately obvious it's equivalent, but really in many models it behaves very similarly, yeah? But instead of d over n, well, let's do one step. Let's say now we still have independent probability of diseasedness, but not identically distributed. So different subsets of your population may be more prone or less prone to the disease, right? Maybe your gender, age, physical location, whatever determines these things, and you can you have that prior information. You have those statistics, right? So what can you say? So and the average number of diseased individuals matters. Now the entropy of this probability vector obviously is a lower bound, right? And in various settings, we can get close to the entropy, adaptively, non-adaptively. So adaptively, you can do some sort of nested testing procedures. There's a neat connection to data compression algorithms, which I, again, super fast. I'm happy to go over it slowly later. But basically, kind of like a Shannon code, you can bound the number of tests required for adaptive tests. Like basically, your intuition is still the same. You do a test, you get a positive test outcome or a negative test outcome. You always want to split your tests so that your conditional probability of a positive test outcome is close to a half, right? So conditioned on your previous test outcomes. That's the intuition here. And then you can replicate this intuition even non-adaptively, but then yeah, you can replicate non-adaptively as long as it's the distribution is not too skewed. So then you can do it. And then not on the slides, but very recently, last ISIT, someone was able to generalize this to many more general settings as well. I'll talk about that shortly. I'll land on this last slide over here. Obviously, too much I've not talked about. So what we talked about, classic group testing, the background, fast algorithms, constraints on group sizes or test sizes, the general noise models, and prior statistics, right? What could still be done? So for example, that last thing I talked about, prior statistics, I assumed independent but not identically different. One could now imagine, like in a population with n individuals, there are 2 to the n subsets, right? And each of these 2 to the n subsets may have some different probability of being the true disease set, right? So now it's a much larger probability distribution. Even describing it takes much more time, right? But the entropy of this probability distribution is still a lower bound on the number of tests required, right? Can you get close to it? And for the adaptive setting with some assumptions, recently a group last ISIT presented something, right? Shireen Bhaktedi at UPenn. The non-adaptive version, I believe, is still open, right? Or at least there are some technical challenges. Constraints on the types of tests. And what I put over there is network tomography. So imagine now you have a network, you have access to some servers on this network, and you can send packets between these things. But your network is not working as expected. So you want to figure out where in the network the problem is. Right? So this is called network tomography. Or maybe you want to figure out the topology of the network. Right? So in this case, you can't choose arbitrary tests. You can only choose those tests where there's a path connecting the corresponding servers, right? So with these types of constraints on tests, it enforces some further constraints on the behavior of the network, which now very much depends on the underlying graph parameters, right? There's some really nice work by Mary Wooters. Well, before that, Saligrama and I forget the author, but then and Cheragachi, but then follow up much nice work by Wooters, but generally speaking, the answer for general graph topologies, I believe, is still open. Okay. List decoding. So list decoding and communication problems often helps, and we are exploring what happens for group testing. And more generally, I view this as a simple example of a general nonlinear sparse recovery problem, inverse problem. Now, imagine you have not just diseased individuals and non-diseased individuals, but maybe some people with resistance in their blood, right? So some positives, zeros, and negatives, right? Larger alphabet. Your test outcomes could be more general as well. Your functions could be more general as well, right? How the inputs are combined to give you the outputs. So this machinery, I believe, lends itself to a very general input alphabet, output alphabet, functional relationship sort of framework. I mean, it'll be a fair bit of work to generalize it. So starting with some classes first would be useful. Yeah. All right, I'll stop there. Happy to take any more questions. I did actually overrun. I was trying, yeah, I'm sorry. Yes? Almost certainly, I imagine, I have not done it, but you can do it live, but if you type Google Scholar group testing, AI, but it'll probably be something. Actually, that'll probably give like false positive type of result. Like it'll give something else, but yeah. But yeah, maybe you can do that for me. So I mean, I would imagine like often the recovery algorithms can be somewhat complicated, whereas with ML, like that'll probably help, right? A different use case, well, Parimal and I are working on using ideas from group testing to boost AI ML, so we'll see. Yes?
Sort of high-level questions. What are the different circumstances under which adaptive testing is most beneficial over non-adaptive? And when does it not prove to be beneficial?
Right. So the question, just in case it needs repeating for recording, when does an adaptive test prove beneficial over non-adaptive, when does it not? So, so firstly, adaptive, so non-adaptive is a special case of adaptive, right? You can always ignore the adaptive part. So it'll never behave worse, of course, right? Adaptive will never behave worse than non-adaptive. The question is, when does, so like basically the problem with non-adaptive tests is like if you were reading the answers sort of sequentially, at some point you may already have learned some things, and because each test is quite large, N over D, necessarily there's going to be overlap between the test outcomes, right? Or between the items tested. So then you start getting correlations between your test outcomes. So that's why when the density is kind of high, you need to do a lot of tests, right? Then you start, then it starts causing problems, right? So yeah, my broad answer is, yeah, the more the number of diseased individuals, then at least instead of a fully adaptive setting, maybe a partially adaptive setting, like first you do something non-adaptive to figure out some large subset of diseased individuals and so on, and then you do something, so 2-stage adaptive, 3-stage adaptive, things like that could be helpful, right? I know there's a question here first, and then, yeah.
My question is on this adaptive group testing. So if you have adaptive group testing and you're doing like sequential tests, are they works considering where people get affected dynamically? Where, for example, you did some tests and people who actually you cleared out like these are okay, these are healthy people, and then maybe after some time they might get not defective but
diseased again, yeah.
Yeah, so in that, like, okay, it's like it will become like never-ending process. So how do we counteract, or what measures we could take? So that probability can say like you decoded everything.
It's a good question. You could pose the problem as like maybe there's an underlying Markov chain describing the infection process, and then how do you do disease monitoring with whatever. I vaguely recall seeing something very roughly like this, but there may be variants of the problem, interesting variants of the problem that haven't been explored, right? So it would depend on your resources available, it depends on the infection rates and all of that. But a related thing would be if you have some sense of community, right? So you know somehow which people interact with which people, model this as hyper edges, and then you know how things are spreading. And again, there's something related over here that you may want to look up in the literature, community aware group testing and things that's cited. So yeah, both of these may be relevant.
I had one quick question. So I think maybe one thing to look at when you're doing adaptive versus non-adaptive would be the time to finish the group testing, right? So when you parallelize, you actually, at the same time, you're doing many more tests, right? When you're doing sequentially, actually it's taking a little bit more time. So if you look at it a bit differently, then you'll be able to say that some parallelization actually helps, right? So it's not just the number of tests, but how quickly you can identify by, like if the parallel test, then you don't consider as number, you just think one time you finish so many tests. That's all it is.
Okay, thanks. Easiest kind of question, but I don't have to say anything in response.
No, but you could, somebody must have analyzed it, or maybe it could be quickly analyzed, right? It should tell you that there is a merit for doing non-adaptive. Or sort of like adaptive, which is aware of this, that I need to finish it. Because you do this just binary division, right? So you're going to do one at a time, right? Maybe the first step is, of course, everybody's giving an either this, like this or that, right? And then you go next step, right? But if you did things on parallel, maybe you go the other way, right? And then you probably finish faster. I don't know. But, right?
Right. So, like especially in the dense regime where you do some level of non-adaptive coupled with some level of adaptive, right? There could be the right answer.
Whenever you do not appeal, it's not thinking of like parallelization, but that is actually giving you gain. So even if you're many tests, but they're running in parallel, so you're saving time.
Yeah. Yeah, that's fair.
Let's all thank the speaker. Thank you, Professor, for a wonderful talk. So if you still have questions and want to have a chat with Professor, please feel free to have it by having a cup of tea. Coffee, yeah, snacks and coffee. Yeah. Thank you all and have a great evening.